Do you want to craft the most valuable machine learning models? If so, then you need to learn the single most important concept in real-world machine learning, the bias-variance trade-off. If you want to differentiate your skills in real-world machine learning, if you want to differentiate yourself from the so-called data scientists, then you got to know the bias-variance trade-off. And here's the great news. I am going to teach you the bias-variance trade-off in this video in a purely intuitive way. No code, no math. My next video in this series will cover some code about how you actually make these concepts real in terms of code. But right now, we need to crawl before we walk and walk before we run. So we're going to start with a purely intuitive introduction. Now, here's the good part. You might even find this video actually quite enjoyable. You might even chuckle a little bit when I use my analogy to teach you about the bias and variance trade-off in this video. Before I dive in, a couple things that I should let you know. First, this video is going to assume that you have the knowledge covered in my decision tree crash course, and I'm going to put a link up to that video up here. So definitely watch that. If you're not familiar with decision trees and machine learning in general, it'll teach you everything that you need to know for this video. Second, if you want to get the PDF of all the slides and follow along with this video, there's a link down below in the description of this video, and I will send you the PDF via email if you'd like that. Okay, so let's go ahead and get started. And the first thing we're going to do is build an intuition regarding the complexity of decision tree models. This is going to be critical for understanding the bias-variance trade-off. All right, so the first thing that we need to do is build an intuitive understanding of the idea of underfitting and overfitting. And the idea of a spectrum, the concept of a spectrum is pretty useful because in machine learning and real-world machine learning, there are no absolutes. So on one end of the spectrum, we have models that are overfitting. And over here, we have models that are underfitting. And in the middle, we've got this Goldilocks zone. And obviously, not surprisingly, where we want our models to be is probably in the Goldilocks zone. But to really illustrate this idea, we can also map the concepts of underfitting and overfitting to model complexity. So simultaneously, we can also think of things as being a spectrum down here, and these things align, right? Overfitting is always associated with more complex models, and underfitting with less complex models. Now, using decision trees as our frame of reference, and they're great for learning these really critical machine learning concepts, is a model that is going to underfit. And I'm going to show you an example of the least complex model that you can make using decision trees. And that is a decision tree that looks like this. These are known as decision stumps. So what they incorporate is just a single decision criteria. All they have is a root node. That's it. And then they make a prediction just based on one check of the data, one feature in your data set. That's it. And then they make a prediction. And generally speaking, decision stumps, a single decision stump, is usually not useful. And I mean, if we think about this intuitively, it makes sense, right? If we have a decision tree that's this simple and it's wildly accurate, why are we using machine learning in the first place? It's overkill, right? I'm hunting a gnat with a bazooka. So at this end of the spectrum, conceptually, in the most absurd case, think of a decision stump, a single decision tree that is astronomically simple. So when we want to incorporate this idea of underfitting and less complex with this idea of a really, really tiny tree. Now, on the other end of the spectrum, we could have a complex tree. And this tree right here is super complex. So complex that I probably couldn't display it on anything other than just a monstrously huge monitor, like 80-inch monitor or something like that. And most importantly, what we want to look at here is this idea that there are many, many ways to traverse the tree. So many, many ways to traverse the tree. So there are many, many different types of outcomes based on all kinds of different combinations of values in the data. So you can see many, many different types of leaf nodes here. And as we get more and more complex, especially with decision tree algorithms, we run the risk of overfitting because if they can, a decision tree will memorize your data. And in fact, in Python, in scikit-learn, the decision tree classes are set up to grow immensely large trees by default, and they are prone to overfitting. So you have to watch that. So this is the mental model I want you to keep in mind for a complex tree, something like this, right? So big that you couldn't even display it on a normal sized monitor. And of course, in the Goldilocks zone, if we have these two extremes, right, we have the decision stump, which is like way too simple to actually be useful in the real world. And then we have, in the most extreme case on the far right side of the spectrum, a decision tree that's memorized your training data set. That's the other extreme. And in the middle, we've got this Goldilocks zone. And not to sound like Einstein here, but the idea is that we need to add complexity, right? We can't stay over here, but we don't want to go way over here. So we want to add as much complexity as needed, but we want our models to be no more complex. And that's where the bias variance trade-off comes in. This trade-off allows us to trade off complexity and underfitting versus more complexity and overfitting to try and iteratively get into this Goldilocks zone. So let's talk a little bit more about what this means conceptually by using a metaphor, an analogy here. And this is a very common one that you see in many videos on machine learning, but I'm going to put a little Dave spin on it, okay? So I say here that this is arguably one of the most important concepts in machine learning, but realistically, it is the most important concept in machine learning. A famous data scientist once said that working knowledge, good knowledge of the bias variance trade-off is what really separates true data scientists from the fakers. So super, super important. So what we're going to do is we're going to use an analogy here of throwing darts. And I'm going to put my little Dave on data spin at this, which is I have decided that I am going to learn how to throw darts because my family's worried about me because I have no life and they want me to get a hobby. So I say, hey, let's go ahead and learn how to throw darts. And maybe I'll join a pub league, right? Where I go down to the local pub, local bar here in the United States, is what we would call it, and I throw darts in part of a dart league. But before I do that, I want to make sure that I don't embarrass myself. Makes sense, right? So I want to practice. So let's say, hypothetically speaking, that I go and buy myself a dartboard from Amazon and buy myself some darts, and I set it up in my garage so that I can practice throwing darts at home. But like a dippy, I misread or I don't pay attention to the official rules, and I set my dartboard at home too high. So I'm practicing for days and days and weeks and weeks and weeks on a dartboard that's too high up. And then I say, okay, you know what? I'm pretty good now. I'm actually going to go down to my local pub and I'm going to throw darts in the dart league. And lo and behold, here's what ends up happening. Notice that these little X's here represent my darts. Now I'm throwing my darts up the dartboard and I'm good. So notice how my darts are all tightly packed together, right? They're very close together. So there's not a lot of variability in my darts, but notice that they're consistently too high. And that's the result of my muscle memory from practicing at home being used to the bullseye being higher up. Well, when I get to the pub, the bullseye is actually at regulation height, which is lower. So my throws are biased. My muscle memory is biased to a dartboard that's too high. Now, this situation where I have this bias and this lack of variability in my darts, not surprisingly, in machine learning is known as high bias and low variance. That's what this means conceptually, right? So when you think about this, think about, Dave practicing against his dartboard that's set up wrong. Entirely possible, by the way, if I ever did something like that. So this is high bias and low variance, right? My darts are accurate, but they're far away from the bullseye. So I'm biased to throw too high, but I'm pretty accurate. Like if I'm targeting what I think is the bullseye up here, my darts are pretty close together. So this situation is one idea that we have in the bias variance trade-off, right? This is one situation, high bias, low variance. Now, not surprisingly, we can expand upon this analogy. So let's say that in the first round in the pub league, this is my dart throwing. And I'm super sad and I'm super embarrassed. So I decide to have an adult beverage to ease my pain. Maybe have a few adult beverages to ease my pain. So we go to round two and I've had a few drinks, let's say at the old pub here. And now this is what ends up happening. So in college, when I was at university, we would call this happy darts, right? I've had a few drinks and I'm a little bit happy. So my darts are a little bit, all over the place. But notice that they're still biased because even though I've had a few drinks and I've got happy darts, my muscle memory is still it's still accustomed to the dartboard being higher. So this situation in machine learning, this idea that I'm biased in my dart throws, but I have happy darts, right? They're a little bit, they're a little bit splayed out in terms of where they land. This is known as high bias and high variance, okay? Which kind of makes sense, right? I'm way far away from the bullseye and my happy darts are all over the place. Now, those are the first two ideas in the bias variance trade-off, right? Our models can exhibit high bias and low variance, or they can exhibit high bias and high variance. And we'll see some examples of this in some subsequent slides here. But moving on, there's a couple of other general situations with our machine learning models and the bias variance trade-off that we need to understand. So next up, let's go back and reset the clock. Let's say that I've learned my lesson and I'm like, okay, I'm not going to compete in the pub leagues anymore until I go back home, fix my dartboard, and practice against my fixed dartboard and get good again. And then I'll actually go out to the pub league. So let's say that I do that. So I go back home, I fix my dart, make sure it's the regulation height, and I practice, and I get this situation, which is what you would expect, right? If I practice a lot against a regulation dartboard, once I actually get back into the pub leagues, I should be pretty good. That's the whole point of practicing. So my darts are all close to the bullseye, and they're tightly packed, right? So not surprisingly, in machine learning terms, this is known as low bias and low variance, okay? So this is good. Right? This is what you want, not surprisingly, right? You don't want your machine learning models to exhibit Dave's darts here, right, that are high bias, and you definitely don't want this, right, where you've got Dave's high bias and he's got happy darts. That's bad. This is what you want. But the last situation is this, where let's say that instead of being sad and having drinks now, I'm happy and celebrating with adult beverages, and I keep throwing darts. So I get my happy darts again, but notice my happy darts now have less bias. They're all inside the dartboard, unlike this situation right here. So this is Dave enjoying himself, having probably too many cocktails, too many beers, whatever it might be, and he's got happy darts again. And in this situation, we would say this is low bias, right? Because notice that I'm within the dartboard here. I'm kind of close to the little, I got 3 of my darts out of right here, 3 of my 7 darts right here are real close to the bullseye, so that's good. But I got happy darts, they're splayed out. So that's high variance. Now, if we take these concepts and we map them to the previous slide, that's when we start stitching together this framework, this intuitive framework for understanding our models. So this situation is indicative of underfitting. So high bias, low variance models typically underfit. Usually means that your models are not complicated enough. They haven't learned enough of the patterns in the data to actually be useful. For example, like a decision stump. Now, reflexively, this is usually the situation with overfitting. Remember that big, huge decision tree that we saw on the previous slide? That big, huge decision tree is going to exhibit low bias because remember, it has all those different leaf nodes, all those different paths through the tree. It's not biased in its predictions. It entertains lots of different types of scenarios because the tree is so big, the structure is so massive, it handles lots of different paths. It also means that it typically has high variance in its predictions. In the most ludicrous case, let's say that I train a decision tree with 10,000 rows of data, and it learns the data so well that it has 10,000 leaf nodes, 1 leaf for every row of the training data set. That would be the most extreme case. But that's a good example of high variance in its predictions. Because it's like, look, I got a leaf node for every single piece of data. I am very, very variable in what I predict because my tree is super big, really, really complicated. So this is indicative of overfitting. And as I mentioned before, low bias and low variance is the goal. I mean, this is the holy grail. This is what we want in our models. Now, let's take these concepts and then map them back again to a couple example models. All right, so on this slide, we've got that decision stump that we saw a couple slides ago. I've just made it a little bit bigger so it's easier to read. And this is a quintessential example of a high bias, low variance model. It's almost absurdly so. And here's the thing. If we consider this decision tree and we look at this particular model and we look at these leaf nodes, what we can see here is that this model exhibits very high bias. Like I said, absurdly so, because it always predicts less than or equal to 50K. Because notice here, the class label in this leaf node is less than or equal to 50K. And notice that in this class, in this leaf node, the class is less than or equal to 50K. So it always predicts less than or equal to 50K. I mean, why even have a decision tree, right? Why even have this root node? This model is completely biased. It always says, I don't care. I don't care how old you are. I don't care how much education you have. I don't care about how many hours a week you work, your gender, your racial designation, anything you can think of. It doesn't matter. I don't care. everyone makes less than or equal to 50K. I mean, how can you get more biased than that? Now, simultaneously, if we also think about it this way too, there's also no variance. I say very high bias and very low variance here. And you could basically say this is the ultimate biased model and this is the ultimate lack of variance, right? Because it always predicts less than or equal to 50K. It doesn't matter. It ignores all of the data. It doesn't look at any of the features. It doesn't really matter. I mean, yes, it does look at this feature, but technically it doesn't matter either because it's always predicting less than or equal to 50K. So this is the quintessential high bias, low variance model. Now, one of the things that you have to realize when you get into real world machine learning is that different types of algorithms have inherent levels of bias and variance built in. So for example, the decision tree algorithm is actually a low bias, high variance algorithm by default. Now you can certainly train it. You can certainly set up a decision tree to create something like this if you wanted to. But in general, the algorithm itself exhibits very low bias and very high variance. This is just an anomaly, essentially. I actually had to tweak a bunch of hyperparameters to actually get it to work like this, to be honest with you. Now, compare that to other types of algorithms. For example, logistic regression, which can also do this kind of like yes-no thing. Logistic regression classically is relatively high bias and relatively low variance. So just know that the algorithms themselves that you use work along a spectrum. And in general, what I tend to find in the real world is that models based on decision trees tend to be the most useful because they are low bias and high variance. So you can actually get them to behave like this if you want to. So they're a lot more flexible. And that's why they're almost, the de facto standard in real world machine learning applied to business data, right? Usually using a random forest or XGBoost or some other decision tree based model. And this is one reason why. Now, we can also take a look at that other tree that we saw a few slides ago. And what we can see here is that this is certainly low bias, right? Because it is creating all kinds of predictions. Now, using the color coding scheme from scikit-learn here, what we can see here is that these guys that are kind of colored blue, are greater than 50K. That's the prediction. So all of these leaves that are blue or bluish color are going to be predicting greater than 50K for the income level here. And all of these are going to be less than or equal to 50K. And again, this data set's based on the decision tree crash course that's up here if you want to watch it. In case this all of a sudden doesn't make any sense to you, go watch that video and it will. So what we can see here is that obviously we have a lot more variance and a lot less bias in our predictions because we do predict some folks make less than or equal to 50K and some people make greater than 50K. And we have many, many paths through the model. Now, in general, when I see a single decision tree of this big, the first thing that comes to mind is, this model is likely to be overfitting the training data. So in general, this is part of the reason why we tend to not use single decision trees in the real world. Single decision trees are great for learning and getting started with machine learning, but in general, we then graduate from individual decision trees to things like random forests and XGBoost. And I do have a video for random forests in case you're curious, and I'll put a card up here as well for that video in case you want to watch it. Okay, so there's our low bias, high variance model. Now I'm using extreme cases to cement the idea. And with all this in place, we can now think about the trade-off. So once again, we're going to use these ideas of a spectrum. So here's our spectrum of overfitting. Here's our spectrum of complexity. Here's our decision stump. And here's our really big model. And then once again, we're looking for models that are as complex as needed, but no more complex. And what we're looking at now is essentially trading off bias and variance, right? Because as you move along this spectrum, your variance goes down and your bias goes up, and then the reverse is true. And let's talk about how you actually do that in practice. Now, we're still going to be intuitive because my next video will talk about how we actually work this using Python code because it'll be all about hyperparameter tuning. And now we're just going to conceptually think about what it means in practical terms to start balancing bias and variance. And to do that, I'm going to use another analogy here. And this time I'm going to use the analogy of you as the teacher. Okay, you can think of real world machine learning as being this idea of the computer, the machine is your student, and you are the teacher or the supervisor. And when you get a model, your model is created from the intersection of your raw training data, the algorithm, decision tree in this case, and your training regimen. Most of this is going to be, most of the bias variance trade-off is going to manifest mostly in the training regimen, because at some point you have to fix your data, right? You've engineered all your features, you've got all your rows and all your columns, but all that's set, your algorithm set, decision tree, classifier, let's say in scikit-learn and Python. And then your training regimen is actually going to determine how much bias or how much variance your decision tree model has. And what we're doing with our training regimen here is using our data to figure out how well our model has learned. So how do we do this? How do we know that, in fact, our model, the student in this case, in this analogy, actually learned? Well, just like with real life humans, we test. That's what we do. We haven't found a better way of doing it. And to allow us to do that, to allow us to test, we have to have some raw materials. And once again, using our analogy here, we can think about how good teachers just don't drop a final exam on their students and say, good luck, right? Here's your 100-question final exam. I hope you learned everything. Good teachers also provide practice to students. So let's think of it this way. Let's say you're the teacher in this hypothetical analogy here, and over the summer break, you created 100 questions for a particular subject you're teaching. So let's say you're teaching history, just making this up on the fly, and you create 100 questions that you can use to teach a classroom full of students history and provide them practice. So you know that you have to test the students at the end of the class to make sure that they've learned. There's no other way of doing it, really, right? Whether it's an oral examination or written, doesn't matter. We test. So you say, okay, cool. What I'm going to do is I'm going to pull 25 test questions, and I'm going to pull 25 questions, and I'm going to make that for testing. You're going to say, look, I'm going to hold these back. Out of the 100 questions that I created over the summer break, I'm going to hold 25 back for me to use as the teacher to test my students to make sure that they actually learned. Hopefully that makes sense. And then you say, okay, now, well, here's the thing though. Do I just give all 75 questions out to my students? Or should I hold a little bit more back? So let's say, for example, halfway through the class, maybe I will give them a quiz. And the quiz is a way of me providing them feedback. So halfway through the course, they take the quiz, and then based on their score, they get feedback around like, hey, Jimmy, you didn't do very well on the quiz. Have you been studying? No, I haven't been studying. Okay, well, Jimmy, this is a warning call. This is a warning. This is a wake-up call for you that you need to start studying harder, right? So we can say, all right, maybe holding some more questions back to do a quiz halfway through the course is a good idea to provide feedback to the students. So graphically, we could represent it like this. And we can say, okay, I've got my 25 questions that I'm holding back for my final test at the end of the class. I'm holding back another 25 questions for a quiz halfway through the course to give feedback to the students. And then this leaves me 50 questions that I can hand out to the students throughout the class. So maybe I give them a certain number of questions every 2 weeks for homework or something like that, right? So they can practice and get better. So hopefully they do well on the quiz and they do well on the test because they've learned things. Now, if we take this general analogy of you as a teacher allocating these resources to help your students learn and map that to machine learning, we can think of this as being our training data. And in classic machine learning terms, this is what we actually use as part of the iterative process of building the best model, crafting the best machine learning model that we can. And then in classic machine learning terminology, the quiz is what's known as the validation set. It's kind of like an interim step to validating that the machine is actually learning what we want it to learn. And then lastly, this thing is known as the testing data set or the test holdout set. Those are all synonymous, right? Testing data set, test holdout, all the same thing. And in classic machine learning, this is literally what you would do is you would take all of your questions, or more specifically in machine learning terms, all of your data, and you would split it out into these 3 distinct sets. And none of the rows are shared, right? They're disjoint. All the rows only belong to one set or the other. And you'd have your training set, your validation set, and your test holdout set. And then you would go do your project. Now, what is super important about this is that we've now gone from 100 questions or 100% of our data, to map it back to something a little bit more concrete in machine learning terms, we've gone from 100% of our data to only 50% of our data. And that's bad because we want as much data as possible to train our algorithms, because the more data they have, the more data we have to train our models, they tend to be better off. So what do we do about this? So a popular saying in machine learning, which is a pearl of wisdom, by the way, is this idea that data trumps algorithm. And once again, it shouldn't be surprising, right? If data are our raw materials for crafting machine learning models, then in general, more data is better. Now, of course, GIGO, garbage in, garbage out, applies here. If you have more crappy data, then you're going to have a crappy model. But assuming that your data has been profiled and is of good quality for machine learning, more of it is better than less. So if we apply this to our example, we want as much practice or as much data as we can get for our models. And we've already seen that we get half the practice here, right? And this is not good. We need as much of this precious resource, this data resource, as we can, because data trumps algorithm. But here's the thing. We cannot sacrifice validation and testing. Now, here's what when I teach students machine learning, I talk about this thing which I call the law. And one aspect of the law is thou shalt test. You have to have a test holdout set, and you can only use the test holdout set once and only once. So that's super important. So this part you can't really get away from. But what would be nice is if we didn't actually need to pull out 25% of our questions or 25% of our data specifically for a validation data set. What would be nice is if there would be some way where we could use all 75 of these questions, 75% of the data, if you want to think of it that way, as part of our training regimen, and simultaneously we get validation out of it. So that way we actually get a lot more data to use with our models. And then in theory, we will get better models. Okay, so let's talk about how we can do that using a technique known as cross-validation. So we can't get away from the fact that we need to have data for final testing. So what we want to do is use cross-validation to actually say, look, can we use all the rest of the data that is not in the test holdout set to get both of this idea of training and validation simultaneously? So graphically, we can think of it this way. So what we do is we say, all right, what we're going to do here is repurpose our data. So I've got a slice here that's 25%, a slice here that's 25%, and a slice here that's 50%. So let me just divide that in half. So graphically, we can represent it like this, okay? So now I've split my data 4 ways. So I've got this slice, and this slice, and this slice. Now, the green slice, as we know, is the test holdout set, and that is the law. You have to have it, and you can only use it once and only once. So we can say, boop, green guy's gone, right? The green slice is gone. We have to pay the testing tax. There's no way around it. So we now have all of this data here. So we have 3 slices, which represent 75% of our data. Okay. Now we can actually use this and apply what's known as cross-validation. And the idea of cross-validation is actually relatively simple. Of the slices of our data that we have left over that are not in the test holdout set, that are not green in our visualization here, we then take one slice and we use it as our validation set. And then we use the other 2 slices for our training. And then what we do is we just rotate which slice is used for validation. And the whole reason why we do this is so that we get more of our data useful for training. Because before, what we did is we said, hey, look, this is our validation set. And then we only have 50% of our data left for training. But now we actually get to use 75% of our data. And let me just show you how this works in practice. So what we're going to do in this slide is demonstrate conceptually how cross-validation works. So what we've seen here is we got to split the data or slice it. And what we can see here is what we saw in the last slide. I got my blue slice, my gray slice, and this kind of peach-colored slice here, okay? Now, each one of these slices or each one of these splits is technically known as a fold. So this is a fold, this is a fold, this is a fold. So since we have 1, 2, 3 folds, what I'm showing here is technically called 3-fold cross-validation. So this number here is often referred to as K. And K is just a variable, it's an arbitrary number. So in this case, it happens to be 3. But I could have K equals 5, and I'd have 5-fold cross-validation. I could have K equals 10, That'd be tenfold cross-validation, so on and so forth. And I'm going to get more into this in my next video in the series here. So in this slide, I'm demonstrating threefold cross-validation. How did I pick 3? Because it fits on my slide. That's it. In the real world, most of the time you're using tenfold cross-validation. That's pretty much the gold standard. So, and I'll talk more about that in the next video. So, but for our learning purposes in this video, threefold cross-validation. So as we saw in the previous slide, I say, okay, cool. I just pick one of the slices, one of the folds, and that becomes my validation set. And then I train a model. So I trained a single decision tree off this 50% of the data, and then I ask it to make predictions against this slice, and I evaluate how good it is. So let's say, for example, I train a decision tree with this data. I ask it to make predictions against this data, and it's 85% accurate. Cool. So I just make it of that, 85% accurate. So against this particular validation fold, the model was 85% accurate. Now, I'm assuming here that we're holding our hyperparameters fixed. And again, I'll talk more about this in the next video, but just assume that we're holding our hyperparameter values fixed. Okay. So, but then we're not done, because what we want to do is we want to use every single fold, every single slice as a validation set. So what I do now is I say, okay, I'm just going to go ahead and train and validate again. But notice that the gray fold is now the validation. So I train a tree on the blue and peach data, and then I ask it to make predictions on the gray validation. And let's say I do that, and this model is 82% accurate, hypothetically speaking, against the gray validation. So I just make note of that. So I got 85 and 82. And then lastly, since I have one more fold left, now the blue guy, the blue fold is now the validation set. So I train a decision tree with these 2 pieces of data, ask it to make predictions against these particular data, and then I record it. And let's say this model is 83% accurate. And then what I would do is I would then average these results. I would say 85 plus 82 plus 83 is what? A little over 83% on average. So across all 3 validation folds, my decision tree model using this particular data set and a particular fixed set of hyperparameter values is around 83% accurate, over 83% accurate. Okay. That's how cross-validation works conceptually. And what we're going to see in the next video is each one of these folds represents a dart on our dartboard, essentially, right? So this validation fold represents a dart, this validation fold represents a dart, and this validation fold represents a dart. And that's how we take that abstract idea of throwing darts at a dartboard to understand bias and variance and the trade-off, and then make it quote unquote real vis-a-vis our work in Python, for example, is that our cross-validation now becomes the darts. The validation folds become each individual dart. And what we can do is we can literally start looking at our darts, our validation folds, and say, how do they perform? Are the accuracy numbers really close together? Are they splayed very far apart? How good is the accuracy? All of this will map to the bias-variance trade-off. For example, the accuracy score itself is your bias, because if you're 100% accurate, that's like hitting the bullseye when you're throwing darts. So if you're on average only 70% accurate, you're biased. You're far away from, you're exhibiting higher bias because you're far away from the bullseye, which is 100% accuracy. And if your folds are wildly apart, let's say you're still averaging 70% accuracy across all your folds, but one of them is 80% and one of them is 60%, those are really far apart, so you have high variance. So we're going to see that more in the next video, but that's how this all maps together, how you go from the intuitive concepts to the reality of your Python code, okay? Your folds are your darts. All right, so as I mentioned, number of folds is referred to as K, and what's super important to realize about cross-validation is it is very resource intensive on your computer. So notice that if I'm using threefold cross-validation, I have to create 1, 2, 3 trees and then average the results. If I'm using tenfold, if my K equals 10 and I have 10 folds, then I have to create 10 decision tree models and then average the results. So cross-validation is super awesome. It's the de facto standard. You're going to do it in your real-world machine learning work, but just know it is very computer intensive, both in terms of CPU and memory on your machine. So if you're working with complex models, complex algorithms, and very large data sets, Your laptop might not be powerful enough, quite frankly. And that's where you might want to use like a cloud-based solution, maybe a VM or something like that allows you to scale up. Okay, so that is the base idea of the bias variance trade-off. You've got the analogy of the darts. Now you know that the darts are also your validation folds. And in the next video, we're going to be talking about how you do hyperparameter tuning to actually see if you can get your darts close to the bullseye and also make sure that they're not splayed out, that they're also very close because you're trying to tune your hyperparameters for low bias and low variance. Okay, if you're interested in continuing your learning, here are some resources. This is a good free book, covers a lot of concepts at a high level, but it doesn't really do a very good job, quite frankly, about talking about bias and variance and tuning and all that kind of stuff. So, this is a good book. It's in Python, but it's not necessarily super useful. Now, this book over here is one of my favorite machine learning books of all time. I love this book. It's freely available. Down below in the description of the video, I will put links to both this book and this book. There's a free version available online for both. The only downside with this book right here, Applied Predictive Modeling, is it uses the R programming language. Unfortunately, I haven't found a lot of really good resources in Python for this stuff, but especially free stuff, free books. R, there seems to be a lot more. Now, the good news is that's not really a problem anymore, right? With ChatGPT, even the free version, you can ask it to translate any code that you find in this book in R easily to Python using scikit-learn, for example, and you're off and running. But what this book is very, very good at is actually teaching you the concepts. The code is almost immaterial, especially now with ChatGPT. It's the concepts that are most important. So these are great books for you. And once again, the links will be down below. Also, if you just mentioning this, if you're not a self-study kind of person, if you prefer a self-paced online course, there'll be a link down below the video in the description for my online machine learning course, along with a coupon code to save 20% off if you're interested in that. And if you're not, don't worry about it. And what I'll do here is I'll put up a tile to one of my other videos on my channel. And when my next video on hyperparameter tuning is ready, which will be in about a week, I'll swap out that video for that one so that you can see it then. Okay, so there you have it. Bias variance trade-off. Very intuitive. Dave drinking and throwing darts down at the pub. Hope you enjoyed the video. Hope you found it useful. And until next time, please stay healthy. And I wish you happy data sleuthing.